This is problem 32.44, and we're going to assume that we have all of the parameters except for C, the capacitance. This is our circuit here, and we start off with S1 and S2 being closed. So this one is S2. Now when these two are closed, the current is just going to flow through the resistor, bypass the inductor, and bypass the capacitor. So then the equation for the current is relatively simple. It's just I is equal to delta V max cosine of omega t, because we're told that's what delta V is here, divided by R from Ohm's law. I'm just going to highlight the answer. So this is I. We're then asked to find the power delivered to the circuit. This is an equation we've seen before, where we have P is equal to 1/2 delta V max squared divided by R. Now things get a little bit more interesting in C, where S1 is now open. So let's go to S1, open that up, and the current now flows through the resistor and the inductor and then bypasses the capacitor. So we're going to have to use a more complicated equation for I, which is going to be delta V max cos omega t plus phi, because they're now not in phase, the current and the potential. And then this is, instead of dividing by R, we divide by Z, the impedance. So then Z, we know, is just R squared plus omega squared L squared, which is XL. There is no XC because remember we're bypassing that capacitor, and this is square rooted. And then phi is going to be the inverse tan of XL, which is omega L, divided by R. So we're going to put everything together and we get I is equal to delta V max over R squared plus omega squared L squared 1/2 cosine of omega t plus inverse tan of omega L over R. So that's our current. Now we can move on to D, where S2 is now open. We're told that V and I are in phase. So what that means is that phi is equal to 0. So there is no phase difference between V and I. This means that we are in resonance. We are asked to figure out what the capacitance is. So let's just look here. We're opening up S2, and now the current flows through R, L, and C. So we have that full equation. If we go ahead and write that out now, phi being equal to 0 means that the inverse tan of omega naught L minus, now we have XL and XC, omega naught C divided by R is also equal to 0. For this to happen, this numerator has to be equal to 0 as well. So that means omega naught L has to be equal to 1 over omega naught C. This is just saying that XL is equal to XC. Now we can go ahead and solve for C, and we get C is equal to 1 over omega naught squared L, where omega naught is just our resonance frequency. We're going to need this result later on, so I'm also going to solve for omega naught, where we have omega naught is equal to the square root of 1 over L times C. Okay, we're just going to hold on to that and use that in the later problem. In E, we're then asked to figure out what the impedance is. So what is Z? Now remember that XL is equal to XC, and because we're subtracting XL from XC in our equation for impedance, we just get X is equal to the square root of R squared is equal to R. And that's it here. E is done, so now we go to F. It says, what is the maximum energy stored in the electric field of the capacitor? So UE. We have an equation that is 1/2 C delta V max, delta VC squared. So that's going to be equal to 1/2 C I times XC squared, where this turns into this just using Ohm's law and remembering that XC is essentially acting like the resistance of the capacitor. Now we want to know I max because we want to know like what is the maximum energy. So that's going to be 1/2 C, and then I becomes delta V max over R squared, and then xc just becomes omega naught L squared. Because just remember, xl is equal to xc, so these two are equal. Now what we're going to do is notice that c is equal to 1 over omega naught squared times L, and we have an omega naught squared times L here. So then when we write that out, we get UE is equal to delta V max squared times L divided by 2 times R squared. We're now going to do the same thing, but talking about the maximum magnetic field stored in the inductor, and that is going to be equal to 1/2 L I squared max. And that is going to be equal to 1/2 L delta V max squared divided by R squared. There's no more simplifications we can do. That's just our answer. So this is what we have here. And we see that, it makes sense that these two are the same because we're saying xc is equal to xl. Now we're going to move on to H. I'll read it out from the problem. It says the frequency of the voltage source is now doubled. So remember, we're in a situation where we're at resonant frequency, so now we're doubling the frequency. They want us to find the phase difference between the current and the voltage. So what that means is saying that, omega is equal to 2 times omega naught. What was omega naught? If we go all the way back up here, this is omega naught. So we're just going to multiply that by 2. So omega is equal to 2 divided by the square root of LC. Now whenever we write out our equation for phi, every time we see an omega, we're just going to replace it by 2 over square root of LC. We have tan inverse XL minus XC divided by R, then becomes, I should replace this here, it's not omega naught now, it's just omega. It's going to be the inverse tan of 2 over square root of LC times L minus, and then we have 1 divided by omega times C, so it's 2 over square root of L times C, all this divided by R. Okay, so we can go ahead and simplify this a little bit, and we get tan to the minus 1 of 2 square root of L over C minus, and then we have 1/2 square root of L over C. So we're able to simplify it out like this, and then we divide all of it by R. We can simplify it once further. I'll just move this down here, and this becomes tan minus 1. And then we have 3 over 2 times R square root of L over C. Okay, so all we did was recognize that frequency being double just means that omega is equal to 2 times omega naught. We knew what omega naught was from a previous problem, so then double it's going to be this. We write out our equation for our phase, and whenever we see omega, we just put this inside here. And then from that point on, it's just going to be simplification a little bit. And that's it for this question. Now, I'll read that out. It says, find the frequency that makes the inductive reactance 1/2 the capacitive reactance. So that's what it says right here. We want XL to be equal to 1/2 of XC. If we just write those out, we're saying we want omega L to be equal to 1/2 1 over omega C. So that means omega has to be equal to, that's not an omega. Omega is equal to 1 over square root of 2 times L times C, or omega is equal to omega naught divided by the square root of 2. Just of course remembering omega naught is equal to 1 over square root of L over C. Okay, that is I, and that is it for this problem.